Okay, in the last video, I got cut off just a little bit at the end. I don't think there was much left. But it comes down to this. If V sub B is your representation of a vector according to some matrix, according to some basis B, and V sub S is your representation according to the standard basis, then if you simply write the basis vectors as columns, then that matrix times your basis representation is going to equal your standard representation. And with practice, it's pretty easy to see why that is. Pretty clear why that's the case. So that if you want to solve that equation, you just invert that column basis vectors matrix and multiply it by your standard basis. You get your multiplied by your vector represented in the standard basis, you get your vector represented in the basis B. And this is something that's familiar. We did this a couple of weeks ago. And in the case of the example we're doing right now, these two vectors were eigenvectors of a certain matrix. So this was your eigenvector matrix. Okay, now this is written out in such a way it might be a little hard to read, so I'm going to kind of rewrite it as I go. But okay, if you got your VS here, your vector represented by your standard basis, and you have some linear mapping defined by some matrix A, then you get your transform vector. And I didn't use a T there, I'm not going to use one now. It's A, VS, okay? A multiplied by VS. These are standard basis representations. Okay? Now, we could also write this vector in terms of another basis, okay? And then we could transform that vector by that basis. But I'm going to call that transform vector T times VV, because we can't multiply this vector by the A matrix. The A matrix assumes that we're multiplying a vector in the standard basis and gives us a vector in the standard basis. There's going to be some other matrix up here that we have to multiply by the vector in the new basis in order to get the transformed vector, again represented in the basis B. Here's our basis B representation. Lose track how many letters I've written, okay? These are basis B representations. Different matrix up here than here. Well, these are connected. The standard basis and basis B representations are connected in one way or another by the matrix P, or P inverse, depending which way you're going. So let's see. If we start with VS, how do we get VB? Well, we multiply by P inverse. So we take VS multiplied by P inverse, we get our VB representation. It's a representation of the same identical vector as we saw before. We had a vector V out here, and we had our two basis vectors here and here. And we saw that we could move along this vector, and then a multiple of this vector plus a multiple of this vector give us this vector, okay? If these are our basis B vectors, then the multiples that we used would be, the multipliers that we used would be our VB representation. Hopefully you understood that when we said it a couple of minutes ago, okay? So, VS is lifted up to the VB representation, same vector, it's still this vector, okay? In our standard space, it was 10, 5, okay? But now it's some multiple of V2 plus some multiple of V1. And those are components VB. Okay. Then there's some matrix here that we haven't figured out that gives us the transform vector, but that transform vector is identical to this vector, has to be identical to this vector. Okay, it's just represented in terms of a different basis. And we can bring it back to the representation in terms of our standard basis by multiplying by P. Okay? So that if we start with a standard basis and for some reason multiply by P inverse, we get the representation in basis B. And then there's some matrix we can multiply by, okay, to get the transform vector still represented in respect to basis B. And then we can multiply that by P to get our standard representation of the transform vector. In that sense then, P inverse TP equals A. Because we start at VS, we multiply by A, we get here. Or we start at VS, I was careless when I wrote that down. Okay, we start with VS and we multiply by P inverse, right? And then by T, whatever it is, and then by P. Okay? Now, more specifically, if we start with VS, multiply by A, is the same as if we multiply VS by P inverse, then by T, whatever T is, and then by P. Now, if we know our A and P matrices, we can easily find our T matrix, right? So our T matrix equals what? Well, multiply both sides by P inverse. Okay, without a lot of explanation, because we're not used to multiplying on the right, okay? Multiply by P inverse on the left, we get T P inverse equals P inverse times A. And then multiply by P on the right, and P inverse times P is going to give us the identity, and we're going to have this, okay? So without going into too much detail, we should be able to understand this pretty easily. So if we wanted to find this matrix T, we could do this, right? Okay. The key is now, if B is an eigenvector basis, T is going to be diagonal. And that's the big, kind of the big deal. Okay. Now there's some qualifications. Eigenvector basis for distinct eigenvectors. You might run into complications if the eigenvectors aren't distinct. Because in that case, they're not uniquely defined. There are many different ways to span the same eigenvector space. Okay, so in that sense then, we've actually got this diagram, but I'm not even going to mention this diagram here. This is sufficient, okay? This is a big idea, okay? And this is the background for how we diagonalize a matrix. Very simple. This matrix is going to be a diagonalized form of this matrix, okay? And the P matrix is just going to be our column of eigenvectors if we've got a complete set of eigenvectors. So it's easy to calculate our diagonal matrix. Okay, and as I say, this is a big deal.